Thank you. So I repeated the abstract on the first page. Topological periodic cyclic homology is the analog of periodic cyclic homology using THH in place of Hochschild homology. If K is a finite field, then smooth and proper DG categories over K satisfy a strong Kunneth theorem. This formula, this is an isomorphism in the derived category of TP K modules. So this is joint work with Andrew Blumberg, and we very recently finished the preprint on it, and it's available on the archive. So in outline, the talk is first going to talk about non-commutative derived algebraic geometry. And what that is about, what this section is about is, well, maybe it looks a bit strange to say DG categories, why DG categories? And also maybe these terms are a bit less well known. And so what that section is to explain both of those things. It's a matter of perspective, and I'll say more about that. And then, of course, maybe unfamiliar is THH and TP, and that's what the next section is about. And then finally, well, this says a strong Kunneth theorem. This may or may not look to you like a Kunneth theorem, and so one of the things I'll do in that section is rephrase that in ways that make it look more Kunnethy, and then I'll also say a little bit about why this theorem holds. Okay, so let me start with talking about non-commutative derived algebraic geometry. I feel like the word derived is necessary, but I think everybody else leaves it out. So the basic objects that you study in non-commutative derived algebraic geometry are differential graded categories, or actually, I prefer spectral categories. So a differential graded category has, instead of having a set of maps, you have a chain complex of maps. A spectral category is the same kind of thing, except instead of having a chain complex, you have a spectrum in the sense of stable homotopy theory. So when we go from HH to THH, we'll go from chain complexes to spectra, and we won't make a big deal about it. If you're not comfortable with spectra, you can think of spectra as being the same kind of thing as homology theories, except you can grip them better, you can do more with them, you can manipulate them better. And if you have a chain complex, you can always turn it into a homology theory by taking chains with coefficients in that chain complex. That would give you a bicomplex, and you take the total complex, and the homology would give you a homology theory. Okay, so I wrote the word small here, and it's easiest to think about this if you think of the categories as being small. Then you can think of them as like algebraic objects. You can think of a category as a generalization of a ring. It's like a ring with many objects. And from this point of view, you have modules for a category. These are just functors. But it's actually convenient not to require these things to be small. And if I don't require them to be small, then I want to put some limitations on the functors I consider. Like I want to consider only functors that preserve directed homotopy limits or directed limits. Co-limits. Like sequential co-limits and bigger things than that, filtered co-limits, that kind of thing, so that somehow the functors are determined by a small piece of the category rather than being big. They remain somewhat small. Okay, but we're not just going to study all small differential graded or spectral categories. We want to consider a kind of equivalence called Morita equivalence, and maybe the best way to explain Morita equivalence is to say again that you can think of a small category as a generalization of an algebra, and you can look at modules over it, and basically what a Morita equivalence is it's a functor that induces, so if you have a functor, you get a functor on module categories, and functor is a Morita equivalence basically when it induces an equivalence of these module categories. So these are also differential graded, and really by an equivalence I mean what we call a decay equivalence or a Dwyer-Kahn equivalence. It's something that's not really a strict equivalence of categories, but on the mapping complexes you have a quasi-isomorphism, not necessarily an isomorphism. Okay, so a basic kind of example is if I start off with a differential graded algebra, I can look at modules over the differential graded algebra, and well, if I look at a module maps from A to itself, that is sort of A, right? If I think of a differential graded category as a ring with many objects, well, if I have just a differential graded algebra, that's a category with one object, and it includes into the module category, and that's an example of a Morita equivalence. And you can do the same thing again, the module category into the category of modules over the modules, and that's a Morita equivalence. And you can see, if you think about this example, you can see that in the case when I'm not small, I need some kind of restrictions on the functors for something like this to be true. And by the same token, if you look at any reasonable DG category, and somehow I want to put, whatever reasonable means, I want to put that restriction on, it's going to be, well, it will be Morita equivalent to its category of modules, and that category of modules will, with some goodwill, will be Morita equivalent to an algebra, which is the endomorphisms of an object in it that generates the category. So, in essence, everything should be Morita equivalent to an algebra, a differential graded algebra. So I'm using this word Morita equivalence, and it might come with some baggage if you're used to Morita equivalences of algebras. So there's this idea of tilting, where if you have two algebras or differential graded algebras A and B, you could look at an AB bimodule and a BA bimodule, and maybe they have the, this probably is supposed to be A. Maybe they have the relationship that when you tensor them over A, you get, well, presumably this should then be B. Oh, goodness, what a terrible slide. Okay, let me correct this. And then, so that should be A, right? No, that should be B, that's the problem. And this should be A, that's the problem. Okay, right, so I can tensor them this way over B, and that could be equivalent to A as a bimodule, let's say, as an AA bimodule. And I could tensor them this way, and that could be equivalent to B as a BB bimodule, and that's called the tilting situation. And this might be what you think of when you think of the word Morita equivalence. This is maybe the picture that you have, and I just wanted to show you that that fits into this picture of Morita equivalence, where we require a map. If you look at the inclusion of A into A modules, that's a Morita equivalence. If you could use the well, it's hard to do it with these wrong. I guess if I look at the functor n tensor over A, that's a functor from A modules to B modules, and that's an equivalence actually, with the inverse being inverse equivalence being tensor over M with B. So that's an equivalence in the usual sense, and then the inclusion of B is a Morita equivalence, and so this is. This tilting situation is a zigzag of Morita equivalences in the context that I'm talking about. So what the goal is, I don't know maybe if this is, I don't know if I can really speak to non-commutative derived algebraic geometry as a field, but at least my goal inside it is to construct and study invariants. And so what that means is I want to be able to construct things for differential graded categories, and I want them to be invariant under, the things I construct to be invariant under Morita equivalences. So one kind of example of this is if I have a differential graded category, if this says subcategory of compact objects, I probably am talking about of the module category. I can take the module category and then just about anything I do with it that preserves equivalences will preserve Morita equivalences of the original object. I can look at the compact objects in it, and I can, there's a notion of the K-theory of this kind of thing, and I can do that. Maybe I should say what compact objects mean. Compact objects mean, if I'm in a category, an object is compact, means that if I look at maps out of it, it commutes with arbitrary coproducts. Yeah, well, arbitrary coproducts. So as an example of this, is K-theory of algebraic varieties. If I look at an algebraic variety and I look at its category of, well, maybe I need some technical hypotheses, but if I look at its category of quasi-coherent sheaves, or I guess I mean complexes of those, the compact objects are exactly the perfect complexes. And so I have a differential graded category of perfect complexes on X. And if I look at the K-theory of that category, that's exactly the K-theory on X in the usual, maybe Quillen 2 sense. Okay, so this starts to suggest how this is something like algebraic geometry. So if I have some kind of algebraic variety or scheme or something like that, I can look at, I'm supposed to plug in categories, and the category I can take is the DG category of perfect complexes. And then for reasonable X, properties of X are equivalent to properties of this category D. So here are two examples. X is proper over spec K. K is probably supposed to be a field here, if and only if when I look at the mapping complex between any two objects, that's a compact differential graded K module. Okay, so let me remind you, compact means that that mapping out of it commutes with coproduct or direct sum. And if you think about differential graded K modules where maps out of it commute with direct sum, those are exactly the guys that are finite dimensional and finitely many degrees. So compact means that if I look at the, if I take the homology of it, remember this is a chain complex, if I take the homology of it and I take the dimension of that and I add that up over from minus infinity to infinity, that ends up being finite. That's what compact means in this case.
When you say in the condition of compactness, you ask for it in the category itself or in the derived?
It's in the derived category. When I say commutes with direct sum, I really mean up to quasi-isomorphism. So it's a compact differential graded K module. I'm looking at the DG category of K modules, and I'm asking for, well, I guess since K is a field, there's not much, I don't have to worry about a projective, cofibrant approximation or something. But yeah, I mean in the derived category. All of this is pretty loose. Okay, so that's proper. An example, X is smooth over spec K if and only if we look at this category. So this is a category. So I can think of it as like the generalization of a ring, right? We think of this category as pretty big, but it's actually small in the technical sense. If I look at its opposite category and I tensor that with it, I can think of this thing as a module over that. So what I'm saying there is, if I look at, I can multiply on the left. I can multiply on the left by D, and I can multiply on the right by D. And so this is a D tensor D module. And smooth, X is smooth exactly when there are some technical hypotheses, but exactly when this guy is compact as a module over this guy. And yeah, I really am talking about the derived category because I wrote Arham on this slide. So here it does matter that I need to take some kind of cofibrant approximation. And so that's what I'm asking about. I'm asking whether maps out of this in the category of complexes here, but I really mean the derived category, commutes with direct sum up to quasi-isomorphism. Okay, so that's not an easy condition to understand, really, especially for a category. For an algebra, it's not so bad. Right. So you can take these are theorems, really, and maybe I should say some names for these theorems. I'm not sure who they are due to. So somehow, I think the vision for this comes from Kontsevich, but if you want to look for a proof, you have to look in papers of maybe Toen or Orlov or Luntz are the names to look for here. But then you can turn this around and make it a definition. And perhaps I meant to define it for categories, but I guess I only defined it for algebras. But you would make the same definition for categories. A is proper if it's so. I've generalized it from being over a field to being over some other base commutative ring or something like commutative ring. It's proper if it's compact over the base, and it's smooth if it's compact as a module over this enveloping algebra kind of thing. Okay, so I wrote on the slide for algebras, but you can make this definition for categories just as well. Maybe it's easier to understand in terms of algebras, right? You can understand what it means to be compact as that kind of module.
So does the switch from 3 to 1 mean that can now not be a field?
Yeah, well, I've made a definition, so I can make it as wide as I want. But yes, it's not a field. It might be a ring, or it might be a ring spectrum. If you want to work with spectra instead of chain complexes. Right, and I don't know whether it's known to the extent to which this definition captures the right properties if you look at the commutative case. So I was able to find it over a field, but people often work over a field because that's comfortable. It might work more generally, or it might not. Yeah.
If A and R are a spectrum,
yeah.
what does the tensor product with an L mean?
Oh yeah. So this tensor product with an L in any case means I'm doing the derived tensor product. So so it could be that A is not flat over L. Sorry, rather. Let's just look in the differential graded case. It could be that A is not flat over R, and then I don't want to really use A. I want to use a version of A that's flat over R when I tensor, and that's what I mean by the L. And it's the same thing, same kind of thing in spectra. So I can't take an arbitrary model of A. I want to take a cofibrant model of A before I smash them together. Does that make sense? Is that okay?
Yeah, cofibrant was the word I was looking for.
Yeah. So L is for left derived. It's like the R on Rhom, except it's an L. Everybody okay? Okay. So anyway, I said a lot of stuff, and I left out all technical hypotheses, and so the results as I've stated them are actually not quite true, probably, but they are morally true, and you can find the technical hypotheses that make them work. But the takeaway for this is that whenever you try and work, the takeaway from this is the perspective that I'm talking about TP from when I start talking about TP. And and in general, for theorems in non-commutative derived algebraic geometry, the statements will be in terms of differential graded or spectral categories, because those are the basic objects. But the results are really about algebraic varieties, because you're going to, and they're generalizations, because probably what you're going to plug in, at any rate, what you want your theories to apply to are the DG category of perfect complexes. But then everybody's Morita equivalent to a differential graded algebra or a ring spectrum if you're in the spectral context. And so the proofs, and maybe to understand the statements, it's enough to just think in terms of differential graded algebras. Okay, so if you don't like differential graded categories, you can always think in terms of differential graded algebras, and you get the meat of the theory. Yeah?
So everybody here is every DC category, comes from a DC curve.
Well, so if I put reasonable hypotheses on X, then yes, right? I mean, if I take an arbitrary, I need to be like, I don't know, if I'm like quasi-compact and separated, then maybe that's enough to be Morita equivalent to an algebra. I'm not sure the exact technical hypotheses. But you know, you need a small set of generators. And I probably want to put that hypothesis in anyway. Yeah, go ahead.
Yeah, I was just going to ask for some flavor of the technical hypotheses before we completely forget about them. So having like a small set of generators is one of these. This is a crappy question.
No, it's not a crappy question. It's just that this is sort of a perspective kind of thing, and it's not. So if the question is about what am I allowed to consider, then I think I want to allow myself to be as general as possible. I don't want to put a priori limitations on my categories. But then if you're asking me when is something going to work, like when is it Morita equivalent to an algebra, then, well, you know, it depends just what you want to allow for your functors. But if maybe I want a finite set of generators, or maybe a small set of generators is enough. Yeah, go ahead. Yeah, so if you're smooth at least, then you've got no worries. So if you got to decide what you want to restrict to, right? You can decide the generality in which you want your stuff to hold. But you know, to understand, you know, to get a first approximation of what's going on, you can just think algebra. Okay. Is that good? Is that a good answer? Okay, so you got a mix of technical stuff and philosophical stuff. Okay, so now, and here I'm kind of reaching the limits of my understanding of this subject, but right, I said you want to plug in the DG derived category of a scheme, and that feels very much like a category and not like an algebra. So how does it become an algebra? And here's just an example. I don't know. I don't know that I want to claim that I understand this variety, but that's anyway. If you look at, for example, PM, then you have the basic sheaf O of -1, or maybe O of 1 is the basic sheaf, and you take its dual, and then you get O of -1, and then you take tensor powers of that, and you get these O of -r's. And if you take the first bunch of them and you take the endomorphisms of that, that's an algebra. That's a differential graded algebra that's equivalent to the derived category of perfect complexes. And as Gonzalo said, whenever you're, I think he said smooth, I'm going to be more conservative and say smooth and proper. You can always find a finite bunch of sheaves to play this game. So here's the algebra that differential graded algebra that you'd be working with. And one of the things that I want to observe from this example is that it's pretty non-commutative, and it's also pretty graded, right? I don't know if it's very differential, but it's at least very graded. If you look at this, then if you look at homology and degree -n, what you're looking at is a matrix of X groups. So this n and this n are the same, and it's this X, right? It's a matrix out of this. This is the ij entry of the matrix if I got my rows and columns right, and I often get them mixed up when I teach linear algebra, but I think I checked this twice, so I think this is right. I was surprised that the I went second, but whatever. Okay, so very non-commutative, very graded. Okay, so next I want to talk about, so this is the, yeah, I'm not going to get that far in this talk, but this is the perspective, and I want to talk about a particular invariant, something that I can plug categories into and will be invariant under Morita invariants, and that's Hochschild homology. And to be honest, I'd have to construct this for a category, and it's not that much harder than to construct it for a category than for an algebra. But my last point was it's enough to consider these. At least if you're trying to prove something rather than to construct something, it's enough to consider these things for algebras, differential graded algebras. So let me just tell you what it looks like for a differential graded algebra. Hochschild homology is built by a cyclic bar construction, which means that if A is a differential graded algebra, this will be a double complex. If A is just a ring, then this is just a complex. But what I do is so I'm making another chain complex. In degree Q, I put Q plus 1 factors. It says Q factors, but then there's one more sitting right there. And I'm supposed to think of these as being in a ring. In a circle, rather. So to speak. And the way I make this into a chain complex is I give it a differential where basically I take the alternating sum of multiplying, where I multiply a guy with his neighbor, right? So I multiply the first two guys and then I subtract multiplying the second and third guy, and I I add the third and fourth guy and so on, and I get to the end and I multiply those. But then I'm supposed to think of these as lying in a circle, so this guy comes around and multiplies with that guy for the last bit of the differential. Okay? Okay, and so I made a big deal about Morita invariance, so maybe I should tell you how this is Morita invariant. And I'm just going to talk about the tilting situation, because to do anything more general, I would have had to give you the category version of this. And this is a good trick to know anyway. This is the Dennis-Waldhausen-Morita argument. So we call it this because in Waldhausen's paper where he talks about this, he says he learned it from Dennis. And then in Dennis's paper, he says he learned it from Waldhausen. So somehow this came back in time and invented itself. It's cyclic. So here's what you do. So this, if A had a differential, then this was a double complex. So what I can do is I can add another complex direction, and I can have the A guys and the B guys give me two different complex directions, right? I can use the number of B's, I can have that be independent of the number of A's, and have the complex go out in two new directions. Okay, and now if I sort of do the spectral sequence of a double complex kind of thing, and I hold one thing steady and look at the differential of the other thing, well, if I hold the B's steady and I look at this part, if I look at the differential here, what that's going to end up being is it's going to look something like n tensor over am, and that's supposed to be equivalent to B. Okay, and so when I hold it steady this way, this is B, and I'm looking at the Hochschild homology of B. On the other hand, if I hold it steady this way, it looks like n tensor over B with m, and that's equivalent to A. And so when I look at it this way, it looks like the Hochschild homology of A. And so this is a thing that maps to both of them by an equivalence. Okay, and so in the tilting situation, the Hochschild homology of A and the Hochschild homology of B are equivalent. Okay, but that's not really what I want to talk about. What I really want to talk about is that this is kind of cyclic, right? There's a, there's a permutation of these guys, and I can just twist them around a little bit. At any rate, the kind of thing that this is it's really a cyclic complex. And when you have a cyclic complex, you have something called Kahn's B operator. And it's a map that is of this form. It lowers degree by 1. Yes, I suppose it does. I'm sorry, it raises degree by 1. That confused me for a second, as you could see. Yes, if you look at what this formula says, it raises degree by 1. And you can use it to construct a double complex. I guess it now becomes a triple complex. If you start with Hochschild homology, you can, this is a differential actually, and it commutes with this differential. And so if you put a bunch of these together, you get a double complex, or if A has a differential, then it's a triple complex. And that, and the total complex of that is something called cyclic homology. That's if you add them on in the positive direction. You could add them on in the negative direction, and then you get something called negative cyclic homology. And this is something that's very relevant to K theory. Goodwillie has a theorem about how the relative negative cyclic and relative K theory are equivalent under certain hypotheses. But why go in just one direction? You can go in both directions, and you get something called periodic cyclic homology. And it's periodic, right? This, you can see that, if you shift it over and up, you're looking at the same thing. So it's periodic, and if you think carefully about that, shifting over is +1 and shifting up is +1. It's periodic with period 2. Okay, so now let me tell you about topological Hochschild homology. What we want to do is we want to do the same thing as Hochschild homology, which happens in algebra, but now what we want to do is we want to take these things in algebra, these chain complexes, and we want to regard them as spectra. And instead of tensoring over the integers or tensoring over some base ring, we want to do this tensor product over the sphere spectrum. So somehow the point of view of stable homotopy theory is that, in algebra, the integers are the initial ring. But in stable homotopy theory, there's a ring spectrum that comes before it. There's an initial ring spectrum called the sphere spectrum. And if you use the smash product instead of the tensor product, you're doing some kind of more basic operation. And that maybe is enough to get you started to consider this kind of construction. And then, the work since then has shown that this is actually a very useful kind of thing to do. It gives you, if you're not working over, if you're looking at something that's not rational, if you're looking at something that has p primary stuff in it, then topological Hochschild homology can give you better stuff than Hochschild homology does. At any rate, we do exactly the same thing, except we work in the world of stable homotopy theory instead of the world of algebra, and then instead of tensor product, we have this thing called the smash product. It's just the version of tensor product that happens in this category. And then what the cyclic structure in Hochschild homology corresponds to is it corresponds to the action of the circle group, the group of unit complex numbers. And that operator, the cons B operator that raises degree by 1, that's like, if you think about the circle, it's got homology in degrees 0 and 1, and somehow that thing in degree 1, that's like the cons B operator, the action of that part of the action. And so you can do the same kind of constructions that you did with cons B operator, except these are, you can't exactly just glue them together. Well, you can. It's a bit of work. I'll say a bit more about what you actually do in a few minutes, perhaps. But you can try to do the same constructions using the circle group action instead of the B operator. And if you do the construction that corresponds to doing cyclic homology, what you get is the homotopy orbits. That's what the construction turns out to be. If you do the thing that corresponds to negative cyclic homology, that's like taking the homotopy fixed points. And if you do the periodic thing, that corresponds to doing the Tate construction, which I'll tell you about in a couple slides. But the point is there is this construction that corresponds to going and doing this sort of gluing thing in both directions. Okay, so you can make this definition. So for a ring spectrum, or a ring that you turn into a ring spectrum, you can define the topological periodic cyclic homology as, so that's TP, as the Tate construction on THH. So why? So we can do this construction, and that's maybe enough to consider it in the first place. But what do you get out of it? So actually, it's only been sort of, this name has, or this notation has only been attached to it recently, but actually it's always been a major player in the trace method K-theory calculations. For example, the Bokstad-Madsen TC calculations and the Hesselholt-Madsen K-theory calculations. It's always been sitting in the background there. There's something called the norm restriction diagram, and this thing sort of sits, a version of this sort of, so that happens for a cyclic group Cp to the n perhaps, but the thing corresponding to the circle sort of sits inside all of them and in many cases controls the calculation. But another idea that's why it's come to prominence recently, and if my abstract in the book mentioned work of Hesselholt, is that the idea maybe advertised by Hesselholt recently that this might be the right characteristic P replacement to use for periodic cyclic homology. And so in his paper, there's some work of Kansky on the, I forgot what they're called, like Sayre factors or something, where they use, they use some combination of HP and HC to come up with some arithmetic formula. And recently Hesselholt has come up with a corresponding formula in characteristic P using TP. Another place where HP seems to play a significant role is in the world of non-commutative motives. Kontsevich, Marcoli, Tabuada, non-commutative homological motives. HP is a major tool in studying them, and maybe TP does something useful in characteristic P, and I guess Gonzalo has recently written a paper that does do something. I'm not quite sure exactly what. But actually it uses the, it's awkward to try and say what when he's sitting in the back row, right? Maybe I should say, I forgot the phrase. But anyway, this new paper. So anyway, you can ask him. This new paper uses the theorem that this talk is ostensibly about, although it's getting unlikely that I'll actually tell you much about it. Maybe I'll just skip that part. Okay, so, good. I forgot that this slide came next, so maybe I will get to tell you about it. So let me tell you about this theorem now. So one of the things that I want to explain in this section is that if you look at this theory TP, it's always, no matter what kind of, no matter what ring you work over, it always is a lax symmetric monoidal functor. I always have this multiplication map. If I have, I guess, X is supposed to be an R algebra or a spectral R category or a differential graded R category for this R that's sitting here. And so is Y. If I have a module, an R algebra X and an R algebra Y, I always have this map from the smash product over the smash product of the TPs to TP of the smash product, and I'll explain that. It's not that complicated. But then the theorem is that if you restrict to the case where R is a finite field, and you look at this functor, I believe this is not a functor but a natural transformation, right? If you look at this natural transformation, then it's an isomorphism. And this is happening in a derived category. It's an isomorphism when X and Y are smooth and proper. And smooth and proper means what I said before. So in some sense, so proper means that these guys are compact over R, and smooth means something about being compact over their enveloping algebras. Yeah?
So isomorphism means for each X and Y there's almost a equivalence, or does it mean more?
So this is an isomorphism in the derived category.
Is it for each X and Y? Or is
This is not functor, this is natural transformation. This is a natural transformation, this is a map. And with these hypotheses on X and Y, it's a weak equivalence. Does that not answer your question? I can try again. For every X and Y, so let me go back a couple slides.
For every X and Y you have a weak equivalence. I'm asking you if it's more than that, if it's something that's independent of X and Y.
So
Weak equivalence in the category of potential transformations.
Okay, so
Later, huh?
so at any rate, the assertion is that TP is a lax monoidal functor, and then you can look at this natural transformation, and you can try and understand it. How far is it from being an isomorphism or a weak equivalence, which means the same thing in this context. And under hypotheses on X and Y, it is one. Okay, so I'll go on. Okay, so I said this may or may not look like the Kunneth theorem to you, and so here's something that will make it look more Kunnethy. So as a consequence of this, maybe I should say if K is a finite field, then one of the very cool things about TP is, maybe I should tell you what TP of K is. TP of K is, or I guess I mean the homotopy groups of TP of K. I take the Witt vectors on K, and then I add something in degree 2 and its inverse. So this is, you start off with something in characteristic P and you get something characteristic 0 out of it. Okay, but in particular, if I look at any particular degree, it's going to be a WK module. So if K is Z mod P, then WK means the p-adic numbers. So ZP or extension. Right, and so here's the nth part of TP, and it's sitting in the middle of a short exact sequence of the tensor product and Tor. So that definitely looks like the Kunneth theorem for something like the integers. Okay, and then if you think about the Kunneth theorem for something like a field, well, actually, you might wonder if there's p torsion. There might be some kind of p torsion, but I can invert p, for example. And if I invert p, then WK becomes, well, it becomes the field. Let's just take the case of K as FP. Then WK is ZP. And then if I invert P, that's QP. And then if I take TP of K and invert P, that's looking at TP star of K. Whoops. And then I invert P. That's QP. of V inverse. Right, and that is a graded field. At any rate, if I invert P, then then torsion disappears, and I get a Kunneth theorem that looks like this. After I invert P, I just get the tensor product. Okay, so let me explain why TP. Oh, I guess I review what the Tate construction is, right? So the definition of TP was that it's the Tate construction on THH, and I explained what THH is, and only by analogy did I explain what the Tate construction is. And to explain what the Tate construction is, it starts with the universal space ET, right? This is the free contractible space with a, it's a contractible space with a free action of the circle group. So one model for this is if you look at the unit sphere in Rn, and you look at that, not Rn rather, Cn, because I want an action of the unit complex numbers. So I look at the unit sphere in Cn, and that goes into the unit sphere in Cn plus 1, and so on. And if I take the union of that, that's a model for this. Okay, so that's how you can think of this. And then what I want to do is I want to take the cone on it, and I make something new called ET tilde. So I take ET plus and I map it into S0, and that's ET tilde. If you want another model of ET tilde, if I looked at the unit sphere in Cn, and I add a disjoint base point and take the take the cofiber of the map to S0, what I end up with is that builds a cone. So what I end up with is the one-point compactification of Cn. So another model for this is you could take the one-point compactification of Cn, and that goes into the one-point compactification of Cn plus 1, and you can take the union of all of those. So that's what that looks like. Okay, so I take this, so this is a cofiber sequence, and I smash it, so I'm going to form the Tate of Z. And I can look at the space of maps from ET to Z, and that's the thing that if I took its fixed points would give me the homotopy fixed points. But instead of just taking its fixed points, I smash it with this first, and then I take the fixed points. Okay? And so if I look at this thing right here, that's the homotopy fixed points. I'm going to tell you about this thing right here, and then this thing here is going to be the Tate thing. Okay, so let me tell you about this thing here. Okay, so that's what that says. Let me look at this thing here. There's something called the Adams isomorphism. This is something weird about equivariant stable homotopy theory. If I take if I smash with ET plus, I get something free. And then when I take its fixed points, there's some kind of transfer that makes it look like the homotopy orbits. And that's called the Adams isomorphism. Okay, so I'm realizing now that when I wrote this slide, I had a different audience in mind. And I probably should have said more here, but I don't actually have that much time. So there's not much more I can say. This is some magic that happens in stable homotopy theory, that if I play this game, it actually turns out to be the homotopy orbits. It's kind of weird and cool. Okay. And so the Tate is defined as this third thing, right? Here's the thing we understand, ish. Here's the thing we understand, ish. And Tate is the cofiber of that map. So if you look at that, what it looks like is this. You have the suspension of the homotopy orbits, and you have a map that you might think of as being the norm. It's some kind of transfer into the homotopy fixed points. And the cofiber of that is the Tate. And this is exactly the same picture as you get with the relationship between cyclic homology. This corresponds to cyclic homology, negative cyclic homology, and periodic homology, right? If you think about how they fit together, they overlap in exactly, you glue the positive cyclic to the negative cyclic along an HH. And so if you look at, when you do that gluing, you get the periodic. And if you take away if you look at the negative stuff into the periodic, what's left is the positive stuff shifted up too. Okay. So this is how you actually do the construction. And now I can explain why TP is a lax symmetric monoidal functor. It's a composite functor of a lot of stuff that I can go through one piece at a time. On the end, I take the fixed points. And that's a perfectly good lax symmetric monoidal functor. If I take the smash product of the fixed points maps into the fixed points of the smash product. Not in the world of stable homotopy theory, that's not an equivalence, but there is a map, and it goes in the correct direction. So that's okay. And then the next piece is smashing with this ET tilde guy. Okay, and if you think about this ET tilde guy, I gave you this model for it, which is the union of the one-point compactifications of the CNs. And if you think about what you end up with at the end, it's something that it has two fixed points, 0 and infinity, but then the rest of it is free. Okay, and non-equivariantly, it's contractible. But if I take fixed points for any other subgroup of T, then it's just the two fixed points, the two things fixed by all of T. And so if I look at that guy, it's got a base point at infinity probably. If I look at him and I smash him with itself, I get another space that has the same kind of property. And in fact, actually, so if I look at ET tilde and I smash it with ET tilde, that's equivariantly homotopy equivalent to ET tilde. And so you can see it in terms of the fixed points, but also in terms of the model you can see it. If I take one-point compactifications and I smash them together, that's equivalent to taking the direct sum of the original vector spaces and then taking the one-point compactification. And so this is sort of like doing the one-point compactification of c to the infinity. And so this is like the one-point compactification of c to the infinity plus c to the infinity, and that's equivalent to the one-point compactification of c to the infinity. Okay, so the upshot of that is, if I smash with ET tilde, that's maybe not exactly on the point set level some lax symmetric monoidal, but this multiplication, I can use this multiplication in this direction, and it's probably not visible, in this direction, to go from the smash product of the functors to the functor of the smash product. I put it inside and I combine these ETs, and that gives me the map that far. So that's okay. Maps from ET in. So I want something like x to the ET smash y to the ET to x smash y to the ET, and I'm not requiring it to be an equivalence or anything. How can I build a map like that? Well, if I move the ET to the other side, I can use the diagonal map to do something like this. So that's okay too. Okay, and then finally, if I look at the last bit, which is THH. THH actually, on the point set level and on the homotopy level, actually is strong symmetric monoidal. It just works. If you think about that, this is maybe some version of the Eilenberg-Zilbert theorem. THH is built as this kind of complex, this kind of simplicial complex, and the Eilenberg-Zilbert theorem says that if I take the tensor product of the chain complexes, that's equivalent to the chain complex of the simplicial complex where I tensor them degree-wise. So you can think of this as that kind of thing. And that's the end. That's how it works. So that constructs the map, at least. Actually, I want a little bit more. I want that constructs the map if I just smash them, but I want to actually smash them over the base, over the TP of the base ring. And so I need a little bit more for that. I can look at this thing. This is some kind of coequal Iser of this thing where I act on the left and I act on the right. And so I can go into here and I can worry about whether it goes into here okay. So I can worry about this stuff, and this turns out to be something about coherence. And if I had more time and if it was, maybe I'll just say for time reasons I won't say anything about that. Okay, so this slide, actually this slide I never had any intention of going through very carefully. It's just here in case people want to ask questions. But I sort of motivated the idea of TP with this picture in terms of HP. And what this slide is about is on TP I have a filtration that looks like this. So if you think about what this looks like, if you think about HP, I have a filtration where, here's the filtration, where the filtration quotients look like HH. And what this slide is about is the same thing happens for TP. I have a filtration where the filtration quotients look like THH. So I'm going to quickly go through that slide. Okay, and whenever you have a filtration, you get a spectral sequence. And if you keep track of the degrees, well, you can see it here. If you look at the E1 term, in each E1 degree, you're looking at THH, but it's shifted, right? Here, if this is, I think this one is the one where it's supposed to be in the natural degree 0. This one's shifted up 1. This one's shifted up 2, and so on. But actually, you can fix this. The same thing happens in algebra. I don't assume that you're familiar with this, but if you are, you know that there's a way of adjusting things to renumber the spectral sequence so that this shifts back down. And the way you do that is, instead of looking at this natural filtration, you just double the filtration degrees. And if you... Sorry, I'll be done soon. And if you do that, what happens is that, because when you do the spectral sequence, you look at the horizontal number and the vertical number you add, that shifts everything down. And when you double the filtration, then you end up with a spectral sequence where it's exactly THH numbered correctly in each even degree. Okay, and so let me tell you about the Kunneth theorem. So you have this multiplicative map, and you have this filtration, and you try and fit them together. And with a lot of work, you manage to do that. And so if you think about that, if the filtration is compatible with the multiplication, then you get a filtration here, and you have the filtration here. And if this is a filtered map, you get a map of spectral sequences. Okay? This spectral sequence on the right is the Tate spectral sequence, which I probably had slides on that I skipped. And yeah, that was the last slide. I didn't skip it. This is the spectral sequence that just looks like THH in every even degree. THH of this smash product, which is the same as the smash product of the THHs. And if you think about what happens on this guy, everything is periodic here. And so if you think about what that looks like, this guy has the filtration here looks like THH in every even degree, and the filtration here looks like THH in every even degree, and you smash them together, what you end up with is a spectral sequence where the, let me skip a little bit further. You look at the spectral sequence, it looks like the tensor product of the associated gradeds. And in fact, without any hypotheses, this map of spectral sequence is going to be an isomorphism on the E2 term. Okay, So that's weird because I did not put in any hypotheses, and I have this map of spectral sequences that tells me these two things should be the same. So at any rate, this is exactly the same situation that you wind up in algebra if you're looking at HP, if you're looking at periodic cyclic in algebra. You can ask if there's a Kunneth theorem, and you can look at spectral sequences, and you look at the spectral sequences, and it looks like that it should just work because when you look at the E2 terms, it's an isomorphism. And so the same thing happens in topology. But what happens in algebra is that, so this, let me go one more so that this thing is not in the way. This guy, the spectral sequence, is always conditionally convergent. But what happens is that this guy, it's not. And you can find examples in algebra when this guy is not convergent, where this map is not an isomorphism, even though it's an isomorphism on the E2 terms. I don't know examples in topology, but what that shows is that there's a burden to show that the spectral sequence on this side converges. And that's where the hypotheses come in. The right-hand side spectral sequence is always convergent. And if we restrict to finite field, for example, and we make restrictions on x and y, then we can prove that the left-hand side is also conditionally convergent. Okay. The end.
So are there any more questions? Yes.
Yeah, you called it the Greenleaf state spectral sequence. I mean, it's not clear to me that that's a multiplicative spectral sequence. Do you need a multiplicative spectral sequence in order to make this?
Yeah, so that's actually a good question, and you've caught me in a lie. So the Greenleaf state spectral sequence actually is multiplicative, but it's not, in order to make this work, we need some coherence on that multiplication. And we don't know how to prove it for the Greenleaf state spectral sequence. In fact, we use a different spectral sequence where we can prove it.
Just do another construction.
What's that?
Just do another construction.
We just do another construction. We use a different filtration where the E2 term isn't very nice, but in fact, this analysis about the E2 terms being an isomorphism, it's sort of easy to explain in terms of the Greenleaf. I mean, I didn't have enough time to make it to make an explanation, but it's sort of easy to see from the periodicity of the Greenleaf state spectral sequence. But actually, it works with it works quite generally. What you need so I mean, it's not really periodicity that matters. It's rather that the Greenleaf state spectral sequence is THH tensor something. And so as long as you have a spectral sequence that looks like that, so that's implicitly an isomorphism, and as long as that isomorphism is coherent enough, that's all you need to see that the E2 terms come together to be the same.
I have a question. In the case when your x comes from the digital of some perfect pair, some smooth and broken scheme of finite field, does TP can it be expressed in terms of some rigorously known homology such as rigid or crystalline, for which the Kunneth formula was already
So it's I don't think it's the same as anything previously known, but it's related to a Talco homology of the derived complex, and so I think that. So I guess I don't know, but that might have a Kunneth theorem along these lines as well.
I ask because I think that for usual HP, this is the case. Because HP
Oh, you mean that it's the same as some kind of derived? Yeah, so this is, so if you think about that, that's sort of related to derived, and this, this at least is not known to be anything already known. Hesselholt, in his original preprint, he called this something like topological periodic cyclic homology, but then decided he didn't like that name because it's not periodic. Although in the case that we're talking about for a finite field, it is periodic. But in general, it's not periodic, so he didn't like that name. And he is now proposing calling it higher derived cohomology. So this is like a characteristic P replacement for derived cohomology, maybe. Sorry, what? Yeah. I'm not sure what higher refers to. And I poo-pooed that suggestion when he told me about it, so I don't know if that's one he still likes. Okay. Yeah, Chuck?
With an eye towards motivic K1 homotopy theory, what do you know about TP of the polynomial ring over the sphere spectrum?
Oh, over the sphere spectrum. I don't know anything about that. It's yeah. So 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 anything over a finite field is going to be 2 periodic, and then so I had a conversation with Thomas Nicolas about it, and he suggested that it should look something like convergent power series, and as sort of the degree 0 part, and then an exterior thing in degree 1.
I suggest we keep asking like questions.